notes for AP Calculus for trigonometric derivatives, I think are kind of fun to show because to me it really shows what you're talking about with slope. So the first ones we're going to start with is just the basic sine of x or theta. It doesn't matter which variable you use. If I want to take the derivative of sine x, so sine x is this line that's right here. And if I think about the slope, there's certain ways you can look at a graph and determine some of the key aspects of it. So when we did this in math analysis, we talked about a sine graph. We talked about the key aspects were the x-intercept. So at 0, at pi, and at 2 pi. It crossed the x-axis. We also talked about the maximum value right here. So at this maximum value, this changes from increasing, positive slope, and then goes to decreasing, a negative slope. Where it changes, if you were to draw a tangent line right there, so if I just draw a tangent line right here, the slope of that tangent line is going to be 0. So the graph of the derivative would have a 0 right there. Same thing happens here. This is decreasing, and then it changes to increasing. Where it changes from decreasing to increasing, the tangent line is going to have a slope of 0. So there is the derivative. And then if you look at this, the derivative is positive here. It has a positive slope. It's increasing. So the derivative is positive. It's going to be above the x-axis. This is all above the x-axis. Right here it gets to 0. This function, this part of the sine wave, is decreasing here. So it's going to be negative. It's going to be below the x-axis all the way till it gets to there. And then right from here to here, the function's increasing. So it's a positive slope again. So what happens is when you graph the derivative of this sine function, here's sine function, here's the derivative, it actually becomes the cosine function. So the derivative of the sine is equal to the cosine. I like showing that. I think that's neat. Same thing happens over here with the cosine. The derivative of the cosine. So here you've got 0. There's a 0. Slope is 0. Here's 0. Slope is 0. There's 0. But now instead of what happens, it's the sine graph would look like this. That doesn't look like a sine graph here. This is going to be negative sine graph. So the derivative is the slope of the function. That's important. I'm going to say that zillions of times. You're going to get tired of hearing me say it, but I want to say it enough where that you don't forget. Horizontal tangent lines have a slope of 0, so the derivative crosses the x-axis at 0. This is important. These two statements are extremely important. We could do the same thing with all the trig functions. Shortcut is just to give you the answer. Or you could take the derivative of tangent and change tangent to sine over cosine, and take the derivative of sine x divided by cosine x, and you can manipulate it to this. You're going to have these memorized. The only way to memorize it is to keep practicing it, but there is some patterns. Tangent and cotangent, when you take the derivative of tangent and cotangent, you're going to end up with either secant squared or cosecant squared. Everything that begins with a c, cotangent, pairs up with something that begins with a c, cosecant. Cosecant pairs up with cosecant, cotangent. Everything that begins with a c, when you take the derivative, becomes negative. Negative cosecant squared. Negative cosecant cotangent. And that works for cosine too. Cosine, negative sine. So now I'll show you these. If I want to take the derivative of 5 sine x, this is just saying 5 times sine of x. So I could say this is 5 times the derivative of sine x. So it's going to be f prime of x equals 5 cosine x. Very simple, straightforward, taking the derivative. The paper's out from underneath here. If I want to take the derivative of pi cosine x, this is just like the first one. 5 is a constant, pi is a constant. Don't forget that. It's not a variable, it's a constant. So the derivative is going to be pi times the derivative of cosine x. So the derivative with respect to x is going to equal negative pi sine x. The next one, I've got a combination of a polynomial and a trig, and that's okay. For the polynomial, we can use the power rule, and for the trig, we're going to go back up here. The derivative of secant is right up here, secant x, tangent x. So that means the derivative is going to equal 2x plus 4 secant x, tangent x. This next one's going to require a little bit more. Sometimes I show this before I show product and quotient rule. In this case, I probably will. So bear with me right now. This has got a quotient, so 1 plus tangent x divided by 3x. So I'm actually going to use the quotient rule. If I haven't shown this to you yet, just follow along for right now. It will make more sense later on. So the quotient rule, I'm going to take the derivative of, or the denominator, multiplied by the derivative of the numerator. So the derivative of 1 is 0. The derivative of tangent x is going to be secant squared x. Minus the numerator times the derivative of the denominator. So the derivative of 3x is 3 over the denominator squared. So 3x multiplied by 3x is 9x squared. I can clean this up a little bit. I notice that 3 is a common factor here, here, and I can remove a 3 from here, factor out a 3. So I'm going to reduce this to y equals x secant squared x. Factor out that 3, it becomes a 1. So minus 1 minus tangent x over 3x squared. I don't know if you remember, 1 plus tangent squared equals secant squared. I could do some rearranging with all of this. Sometimes it has a purpose, sometimes it does not. For right now, I'm not worried about that. I just want you to be able to take the derivative of the trigonometric functions. There's 2 on the back. The first one has got a function theta squared minus 3 theta. And you'll notice I did switch to thetas, just I want you to see it. Most of the time, in most AP tests, they use the x as a variable, but theta is very common variable. There's nothing wrong with using it. This I plan on teaching right along with this. So this is going to use the product rule. So with the product rule, I'm going to take the first function times the derivative of the second function. So the derivative of cosecant theta is going to equal negative, oops, it's on this side, negative cosecant theta cotangent theta. Plus the second function, so plus cosecant x, or cosecant theta, times the derivative of the first function. So 2 theta minus 3. And I could clean this up a little bit. I don't think it's going to get me anywhere, but if you're not comfortable with that, we can distribute. So theta squared times all this will be negative theta squared cosecant theta cotangent theta.
Call from Commerce to MI.
The negative 3 theta multiplied by all this is going to be positive 3 theta
Call from Commerce to MI.
cosecant theta cotangent theta. Cosecant theta times 2 theta would be plus 2 theta cosecant theta. Negative 3 times cosecant theta would be negative 3 cosecant theta. I do that often. I forget about the c with cosecant. Okay. I look around, there's no common terms. I mean, I could have gone back to this and factored it. It doesn't matter what your final answer was. Either one is fine. I mainly want to show this one to show the product rule. And then the last example I have, number 6, I've left no room here to use it, so I'm just going to write it down here. And I have y equals cotangent x plus 4 tangent x. I don't have a product rule. These are being added. I don't have a quotient rule. There's nothing being divided. So this is very straightforward. The derivative of cotangent x, remember this begins with a c. So it's y equals negative cosecant squared x. Derivative of tangent x is secant squared x. So I get plus 4 secant squared x. I probably could rearrange this 100 different ways, but it doesn't serve a purpose. I'm going to leave it like here.